In this video, we're going to look at some of the structural changes that happens to hemoglobin when it binds oxygen. So in the previous video, we talked about how hemoglobin has two stable states, oxyhemoglobin and deoxyhemoglobin. And so when we talk about these states, we actually will be calling them either the relaxed or R state and the tense or T state. And this nomenclature is used for a lot of proteins when you're talking about them having a ligand bound or not. And so the way I remember this is if you're in a room full of oxygen, you're very relaxed. Everything's going okay. While if I put you in a room full of, and there isn't oxygen around, then you would be very tense because you are going to suffocate soon. So tense, no oxygen, relaxed, oxygen. And we're going to look at structurally what happens when we bind oxygen, because that will shift us from the T to the R state. And so in this image, blue is going to be your tense state, like blue blood. Red is going to be your relaxed state, so your oxygenated blood. So what happens when O2 binds? First, this iron this iron is being pulled down. So if you look at the iron from blue to red, it is pulling down towards the oxygen because you have a plus and a negative polar negative charge and a cation interacting, so they want to come closer. When that iron comes down, these porphyrin iron bonds are shortened to move into the center of the ring. And you have a dome that's kind of encapsulating this oxygen. Well, this iron is also hydrogen bonding to this histidine, so that histidine is taken along for the ride as well, being pulled down by this iron. By pulling this down, histidine's on the F helix, your whole F helix will actually twist and tilt down by roughly 1 angstrom. So by this oxygen binding, you're kind of pulling this whole subunit along because it's attached to the iron, and the iron wants to bind to oxygen. Now, how about the interfaces? So we talked about on a previous video how hemoglobin is a tetraprotein, and it has alpha and beta subunits, and they interact at the between alpha 1, beta 2, alpha 2, beta 1, and alpha 1, beta 1 as well. So we're going to look at alpha 1, beta 2. In the T state, you have histidine 97 interacting with threonine 41. And what happens in the R state, along with that whole F helix moving, you have the histidine moving up to now contact threonine 38 as well. So you have this huge shift in your beta to alpha 1 interface. And this is one way that hemoglobins can quote unquote talk to different subunits. By having this change, you are telling the other subunit on this alpha 1, hey, I have bound oxygen, there's oxygen available, get ready to bind oxygen. You also have interactions at the C terminus. So in the tense state, arginine 141 in the alpha subunit and histidine 146 in the beta subunit, they're in this nice ion pair network. However, in the R state, from that movement of oxygen binding, these networks are actually broken. So you break this ionic network. Again, that's a signal to saying there's oxygen around. Let's all shift more to the R state so we can get ready to bind oxygen. So a big summary of the structural change in hemoglobin. Hemoglobin, the 4 subunits are very tightly coupled or connected together. When you get a large change in structure of one subunit, tertiary change, you get a quaternary change in the entire structure. And there's only 2 forms of hemoglobin that can exist, the T or the R. And that's because of that switch we saw in the alpha and beta subunit. So I'll go back to that slide right now. Here, histidine 97 can only be in 2 positions, down here or up here. And this corresponds to T into R. So hemoglobin can only be in those 2 positions. Now the T state has lower affinity for oxygen, mainly because the iron is farther away from oxygen. So it's less energetically favorable for that oxygen to bind than in the R state, where the iron is closer to the oxygen. Now when iron moves into the ring, you have this alpha-beta switch that happens that we saw in the previous slide, and your C-terminal ionic network is changed. This is a signal to the other subunits that oxygen is available, and they all will switch into the R state, making it more likely that oxygen will bind. The affinity for oxygen increases, and this is what we call positive cooperativity. And that's it for this video. I will see you in the next one.